Hello friends, welcome back to my channel, and today we will be going to start cache mapping. Okay, so before starting with cache mapping, let us try to recall what caching was. This is our CPU. Inside this CPU there are small memory locations register, and this is our RAM where our actual program which is running is stored. This is our RAM, right? Or memory. So this is our these are our instructions I1, I2, I3, so on. Okay. Now this accessing now the program CPU will have a program counter register as well, and it will one by one the address of the next instruction to be executed is written inside this program counter. But accessing this RAM memory is very huge and very slow. So the time required to access a register which is inside a CPU is very less. But the time required to access the main memory is too high. So if we want to reduce, our goal is for increasing performance, we need to reduce the average access time from memory. So for that we introduce a memory hierarchy out on this, and this cache, that is known as a cache memory. This cache memory is on the same CPU chip but outside the CPU and is faster than the RAM. Access on a cache is faster than a RAM memory. So what is the idea is, whenever we require some instruction from the memory or data from the memory, first of all it will check, the CPU will check whether that memory address data is present inside this cache memory or not. If it is present inside this cache memory, it will fetch it from here. And as this cache memory is small in size as compared to RAM, everything we cannot store inside this cache. So at that time, when there is a cache miss, then what do? We go to the main memory and fetch that data or instruction from the main memory. Now you can see here, earlier you for everything you were going back to the main memory, but now the main memory access is becoming very less as some of the frequently accessed data and instructions you are keeping in the cache memory which is near to you. Okay, so now the question is, okay, sorry, let us go to the next page. The question is, how do we now CPU, it will generate RAM memory addresses, right? Let's make the CPU nicely, a nice CPU. Now the processor, okay, let us call it a processor. The processor, it will generate RAM addresses, right? RAM address. Actually, it is generating logical, go to that detail right now, okay? It will generate memory address of instruction I1, suppose, in this RAM. Okay, this is your memory. So let us make a bigger memory. Okay, this is your memory, this is your memory. Okay, now processor in its program counter, it is storing the address 1001. For example, this is address 1001. Okay, okay, let us for right now, let us take decimal addresses. Okay, then after finding the pattern we will write the binary addresses. Okay, let us write decimal addresses for now. Okay, the addresses suppose are 0, 1, 2, 3, so on. And in program counter, suppose we are trying to access address number 3. Okay, so the question is, now this is your cache memory, right? This is your cache memory in between the processor and the main memory. Okay, now the question is, you have generated an address for which is an address of the main memory 3, right? Now this address, we know only this CPU generated address. How do we know this, what address on the cache? Cache will have some addresses, right? 0, 1, 2. These are the 3 indices in our cache memory. So inside, now using this main memory address, how do I know in which address this data is present or not? Where to look in the cache memory, where this main memory address number 3 is present or not present. So this concept, that means we have to find a pattern, right? We have to find a pattern in this address 3. To translate it to a cache memory location, we have to find a pattern. Okay, how this will be mapped? So for that, there are 3 cache mapping types. Okay, cache mapping types. First is your direct mapping. Second is your set associative mapping. Okay, and third is your fully associative mapping. Okay, in this video we will see only the direct mapping. Okay, so let us begin that. Okay, let us go with the direct mapping. Okay, okay, so in direct mapping, what happens, one main memory block will be mapped to one cache memory block. Okay, this is your cache memory. Let us take 4 for example. We will take, there in cache memory there are 4 indices: 0, 1, 2, 3. Each of these cache memory, I will write cache memory for short as CM. So each of these cache memory indices, they are called as cache memory blocks or lines. Okay, CM blocks or lines. Okay, I'm not writing it. Okay, hope you understood. And let us write the main memory blocks now. This is your main memory block. Okay. 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 Okay, this is our main memory. And in main memory, we have suppose from 0 to 99 indices. 0, okay. 0, 1, 2, 3, so on till 99. Okay. This is our main memory blocks. Okay. Same as the cache memory block size, we create main memory blocks. Okay. Each block will have, for example, let us take the block size. Let us take the block size. Okay. Yes. Okay, let us take the block size. Let us talk about the block size a little bit later. These are the main memory blocks, and each main memory block will contain certain number of bytes. We will see that a little bit later. First, try to identify the pattern of the mapping. Okay. The question is, for example, you have to okay, let us take this example. This is a better example. Let us take the cache memory size, the blocks in cache as 10 from 0 to 9, and the number of blocks in cache as 10. That means we have 0 to 9 indices over here. So on till 9. Okay. Okay. And in blocks in main memory as 100, 00 to 99. Okay. Now observe. Now how will the main memory block addresses be translated where it will be kept inside the cache memory in which index? So let us say that one main memory block is mapped to one cache memory block based on how we are deciding. We will take the main memory block address and modulo it with size of our cache memory. Okay, this is the logic how one main memory block is kept inside the cache memory. Okay, all right. Yes, now let us try to identify the pattern. Okay, 0, 1, 2, 3, 4, 5, 6, okay, 7. I'm not drawing the whole table. Okay, what we are doing, we will write the cache memory where it is mapped and the main memory address. Which main memory block addresses are mapped to which cache index? So we have total 0 to 9 cache indices. So 0, 1, 2, 3, 4, 5, 6, 7, 8, one more, 9. These are the indices, and the main memory. Okay, and as we have main memory indices from 00 to 99, right? 00 when modulo with 10 will give us 0 only. 01 on modulo with 10 will give you 1, right? 2, 3, 4. 4 on modulo with 10 will give 4 as remainder, right? 5, 6, 7, 8, 9. 10 on modulo with 10 will give 0 as remainder. 0, 0. Oh, sorry, 1, 0. Yes. 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9. Right? 20 On modulo with 10 will give 0, 21, 22, 23, 24, 25, 26, 27, 28, 29. Okay. Now can you observe? Okay, one more we will write. Okay. So on till 90, 91, 92, 93, 94, 95, 96, 97, 98, 99. Okay. So these main memory block numbers are mapped to these respective cache memory block number. Okay. Suppose the CPU request for main memory block number 38. Where will it be mapped in the cache memory? Which cache memory block it will be mapped to? How to find the pattern? I know we have to take a modulo with 10. So it will be mapped to cache memory number 8, right? But in the binary also, how do we find which bits of the CPU request main memory block number will be for which cache memory block, and which bits will be used for tag identifier? Okay. Observe over here the LSB bits. The LSB bits for uh, all these main memory blocks with which have 0 cache memory block number, they are same, right? Here also we can see the LSB bits are same as 1, right? So what we can do, the LSB bits we can use as cache memory block number, right? And what about the MSB bits? The MSB bits for all these main memory blocks are different. So we can use the MSB bits. Suppose, for example, as we have 99 total main memory blocks, right? 99 total main memory blocks, but only 9 cache memory blocks. So we can have two blocks, main memory blocks, which are mapped to the same cache memory block. We can see that 00 and 10 both are mapped to 00 and 10, both are mapped to cache memory block number 0. So to identify whether which main memory block is kept in 0, whether it is 00 or 10, because data in both will be different. So to identify it properly, we can use identity card, or what is different between 00 and 10. The different is their MSB bits. All their MSB bits which are mapped to the same cache 0 are different. So we are using that MSB bits as, so we will use their MSB bits as tag, or like a Aadhaar card, a unique identifier. For example, in this 0th cache memory block, 10 is kept right now. So what we will do, we will keep the MSB bit 1 as its tag bit. As we know, it is unique. Okay. As we know, in all the blocks which are mapped to 0 cache memory line number, they are having their MSB bits different. So it can be uniquely identified. Okay. Next. So in the next video, we will see how in binary we can translate this information. Okay, bye bye and take care. Happy coding.